Guys, so as we have completed the chapter AC, and we have mentioned the entire thing which is required from the chapter in the live class. So today we'll be starting with EM waves, which is electromagnetic waves. EM waves. It's one of the simplest chapter for your 12th entire syllabus of physics. And happy news, least amount of marks comes from this. That is in CBSE point of view as well as NEET or any entrance examination. EM waves is one of the easiest chapter because it doesn't or a very least amount of questions. I can say very rare questions come from EM waves. CBSE except only 2 or 3 marks, not 3 marks probably 2 marks. Questions comes up. As you can see in your textbook, it has the chapters of only 19 pages. So as you can see, just one of the smallest chapter, so very easy to study. So let's move on with it. Okay, so as we start with EM waves, first question is, what do you mean by EM waves? Now from the name itself, it suggests it's a combination of electric and magnetic waves, right? Electric waves and magnetic waves, or I can say electric field and magnetic field. So when we have a combination of both electric field and magnetic field, they occur or we see them in a waveform. Hence the combination of electric field and magnetic field is known as electromagnetic waves. Clear? Now it is something which we have seen in our daily life, something which you see throughout your life, guys. See, even if see how you are viewing the video which your teachers are uploading, or this video which you are watching is also a application of electromagnetic waves, right? Or see, or you boys might be much more interested in submarines or flight cases. I'm not telling you guys that girls are not interested. I'm just giving a proper example. Submarines, flight, etc., navigation is required, right? So or a person say a person or you can say there is a flight from say Russia to India, and another flight is going from India to Russia, so they shouldn't collide with each other, right? So there will be some operators who will be near to the airport itself, and they are the guys who will be navigating the, or they will be the persons who tell the route of each plane, or how much feet they are above from the level ground, right? Ground level, etc., is told by the engineers or the technicians who are sitting over there, right? So how can they no measure this special distance, or how can they say how much distance the flight from their ground is? This is something can be measured by using the help of electromagnetic waves. See, earlier in old saying, you can see some of the YouTube videos itself that when you go for history, how earlier, that is in 18, I can say 19th century itself, the starting time when the flight was not that much or famous, or I can say is very costly. At that time, there has been a lot of accidents, right? In such a way that the two flights, right, they come on the same path and they undergo collision, right? This and all happened just because of the negligence or from the technicians who were supposed to tell the route, right? They were supposed to sell the flight from the which were traveling in opposite directions, and they were supposed to inform them how much far they were from each other, right? So this and all happened because of technical problems, right? This and all now doesn't happen, right? It's very rare. Yeah. So moving on, so there is a wide application of electromagnetic waves. So this chapter is something which is very close. Most of the chapter which you have learned till, yeah, I can say 11th or 12th is rarely some comes or you have seen in your daily life, right? So electromagnetic waves, this chapter is something which you relate with your daily life, right? So submarine navigation, flight navigation, even in the medical field, right? X-rays, right? Laser treatment for your eyes are all electromagnetic waves. Your radio signal, TV signals are all electromagnetic waves. How does the traffic police detect the speed of vehicles? You might say then they will have speed detector. How does the speed detector detects the speed? right? This and all are the application of EM waves. Even your TV remote, IR radiation, right? IR communication, this and all you would have seen in some of the mobile also. Earlier the mobile sets could transfer data from one mobile to another through IR communication only. Then only this Bluetooth etc came up, right? Then similarly LEDs, microwave ovens, mobile communication etc are all actually the application of electromagnetic waves. So if any person asks you what are electromagnetic waves, then we can see that we know the electric field can generate magnetic field. Similarly, the magnetic field can generate electric field, right? It's a vice versa process. Hence, electric field or electromagnetic waves is actually coupled time varying electric and magnetic fields that propagate in space as waves. What it is said? They are coupled. Coupled means, you know what is coupled, right? Combination of two. Coupled time varying electric and magnetic fields that propagate in space and in the form of waves. Clear? And how does that waveform looks like? Either you can take the examples of your net itself, or you can say if this is my any field, let's say it's magnetic field, then this is how the electric field will be. They're perpendicular to each other, right? Like this. Clear? Very easy. If you want, I can take from net itself. Took from the net and I just pasted it so that you guys can properly understand how the electromagnetic waves look like. This blue lines indicates the electric field and the red lines are for magnetic field. So the red wave is for magnetic field and the blue wave is for electric field. You can see they are propagating perpendicular to each other. Clear? Right. So actually this magnetic field section etc was broadly, or I can say was actually told or completely and made understood by a person called Maxwell. So Maxwell was the major contributor in the case of electromagnetic wave study, right? So for studying etc he did an experiment also, right? So that experiment we'll talk about now, which is not Maxwell experiment, right? Now he proposed, he made first, before he, what and all picture are coming, I'm sorry guys, okay, I will not take that part. Okay, so Maxwell experiment, he made a proposal, right? We all know that magnetic field generation, or I can say time varying magnetic field generates electric field, right? And it was stated by whom? Faraday. As well as lenses gave the direction how that electric field will be, or the current due to that electric field will be. And also we learned that time varying electric field will generate magnetic field, right? Now Maxwell worked on actually the inconsistency of an Ampere circular law. You know Ampere circular law, right? You studied about it, right? So Ampere circular law, he said that there was some inconsistency. He didn't say that it was wrong. He just said that there are some gaps in Ampere circular law which was supposed to be filled. There are some inconsistency. So Ampere circular law had some inconsistency which was totally corrected by Maxwell. That's why later on Ampere circular law was named as Maxwell-Ampere or Ampere-Maxwell's equation, right? That and all we will describe later on. Just move on now, right? So what did Ampere circular law state? It stated that integral B dot dl is equal to mu 0 I enclosed in the, right, in the surface, right? So what was actually Ampere circular law? It was actually a law which was used to make Biot-Savart's law simpler, right? So Biot-Savart's law was made simpler by using Ampere circular law, right? So if you have uniform or non-uniform surface, you consider a uniform loop or a surface which is non-uniform, right? And we consider a surface or a loop that is known as Amperian loop, Remember, this and all I have taken earlier itself. So an ampere loop is considered. He said that the integral of magnetic field dot the dl surface or ds, it is actually length, right? Then it is equal to mu 0 times current enclosed by that loop, right? Now Maxwell noticed some inconsistency in this. That is, the law is not always true in all conditions. He proved it by some experiment, right? For that he took a scenario. Who? Maxwell. He said that suppose I have a capacitor like this and I have charged it. Say this is positive terminal section plate or this is negative plate and a current is flowing, right? And he was going to find the magnetic field at P at different conditions, right? He was going to find what? Magnetic field. Actually he is going to take two conditions, right? For those two conditions he is going to consider two different kinds of Amperian loops, right? So what does the Ampere law say? Any loop you consider, the end result of that is integral b dot dl will be mu 0 I enclosed. So even if you consider an Ampere loop like this, like this, like this, what and all condition is that integral b dot dl will be equal to mu 0 times current enclosed. What it doesn't depend upon what is the type of Ampere loop you are considering. Clear? Right. So he first took an example. Suppose he took a first condition, right? This is our, as per him, this is the capacitor. This is positively charged like this. This is negatively charged. And he considered a point like this here, right? I said that suppose I am going to consider a loop like this. This is my Amperian loop, right? He said that would and the current is flowing like this. Right, what did he say? So integral b dot dl, this closed integral, right, is equal to mu 0 I. Now b is constant, he took integral dl is equal to mu 0 I. And what does the integral dl say? The Ampere loop is having radius r, right? Then b is equal to integral dl is the circumference of the loop, right? That is under length. That is 2 pi r is equal to mu 0 I, or he said b is equal to mu 0 I by 2 pi r. This is the magnetic field at P as per him, right, or as per Ampere's circular law. Now what he did, he took in another scenario, right? He said this is again the same capacitor, this is plus charge and this is negative charge and the current is flowing. And he told that I am going to consider an Amperian loop like this. Like suppose this is a box and this is our point P, okay? And the P, this section he is going to open. This just like this is a shaded section, okay? This shaded entire portion is just like a box and that box is acting as the Amperian loop. Clear? And this Amperian loop is acting like a box with open lid. Right, that lid is this one, right, and inside that lid, so I can say this P is actually enclosed inside the surface itself, but just this section is open. Clear? Right, so I can ask, if you are asked this Amperian loop, if it is enclosing the point P, yes, it is enclosing. Clear? Right, this much clear. So for this Amperian loop, you are going to write the same equation. Integral closed integral b dot dl is equal to mu 0 I, right? Again b closed integral dl is equal to mu 0 I. Now this loop is an Ampere surface and inside the capacitor, right? Loop is an Ampere surface and it is inside the capacitor, and you know the capacitor is having fixed charge, right? Fixed charge means there is no current, right? No current means this entire term goes 0. So this term is 0 means integral b integral dl is equal to 0. Integral dl can never be 0. That means b is equal to 0. Clear? So if b is equal to 0, I can easily say that, see, we consider the magnetic field at the same point, right? Same capacitor, same point P, and we found two different values for the same P. P initially have the magnetic field as how much? Mu 0 I by 2 pi r. This is for the first case, but for the second case it has B is equal to 0. For the same point there are two values of magnetic field which shouldn't exist. There should be only one value. So how did this happen? Because we consider two different types of Ampere loop. Right, so two different Ampere loops cause two different magnetic fields, means the statement said by Ampere circular law, that is, if you consider any type of or Ampere loop will produce the same value of integral B dot dl is wrong. Right, clear? Right, so Maxwell started to correct the Ampere circular law. Right. The next heading, please write it as Maxwell's correction of or to Ampere's law. Clear? He said that the Ampere circular law may not be wrong. Right? There might be. See, he said that, what was his statement? Remember? The capacitor, right, the current was there. So the same point P had two different of magnetic fields, B1 which is mu 0 I by 2 pi r, and the B2, or I can say second condition, had magnetic field 0. Right, so this was the experiment he told. So he told, why did the current or B2 become 0? Because the Ampere loop, we consider this one, and this section has no current enclosed, that means magnetic field is 0. Right, now he stated that might be the Ampere loop law is not wrong. Right, that is, we consider that there is no current inside the capacitor. Right, so he said that there might be some current in between the plates of the capacitor. He assumed that there are some current inside the capacitor. Now if he's assuming and he was telling that there is a current in the capacitor, then he has to prove it. Right, how can there be a current inside the capacitor when we know that capacitor has fixed amount of charge? It can charge and discharge, right, but that charge, we, as per we initial condition, this charge is fixed. Right, now he knows, or he said that, Maxwell said that, we know there is an electric field inside a capacitor. Remember, this is a capacitor, positive charge, negative charge, and electric field is from positive to negative. Right, and what is the magnetic direction? We know it is from positive to negative, and this electric field is perpendicular to the plates. Right, but what is the magnitude of electric field? I will write epsilon. Electric field is V divided by D, potential difference between the plates divided by distance between the plates. Let's say the capacitor is having the capacitance C, and its area of cross section is A, or area of the plates is A. Now, what do we know about the potential difference? We know V is equal to Q by C, where Q is a charge stored. Right, so I can write epsilon is equal to, in place of V I am writing this one, Q by C, and then there is a D. Right, now what do you know by a parallel plate capacitor's capacitance value? It is A epsilon naught by D. Right, so I am going to substitute this value here. So it becomes epsilon is equal to A, right, or sorry, epsilon is equal to Q divided by A epsilon naught by D into D. So D cancels, so I can get Q divided by A epsilon. So what is the magnitude of electric field inside the capacitor? It is Q divided by A epsilon naught. Oh, there is a problem, right? Write it as capital A itself, because then we will make confuse it with epsilon naught. Right, so here let me write it as capital E for electric field, capital E, or you will make mistake with permittivity. Right, clear? Electric field, write capital E itself in here. Clear? So that means this much amount of electric field is stored inside the capacitor and flows from positive to negative plate, and is perpendicular to the plates, surface of the plate. This much clear. Right, but we know that epsilon naught is equal to 0. What is this when you consider the capacitor like this? There is only electric field, that is q by a epsilon naught inside the capacitor, and it is from this direction to this. But here there is no electric field, and there is, oh, again I wrote it epsilon E, right? And here also electric field is 0, right? If there is no electric field here, that is no electric field is entering, no electric field is leaving, means that electric field has been generated inside the plate itself, right? That is, this electric field is only inside the plate. Clear? And if there is electric field and there can be change in electric field, how? See, this capacitor, once it is charged, later on it starts to discharge, right? So there is a variation in what? Electric field. There is a potential difference, right? So one positive plate will be losing its positive charge, and a negative plate will be losing negative charge. So there is a variation in what? Electric field. So due to electric field change in the capacitor, there can be what is known as electric flux, right? Due to change in electric field. So what is the expression for electric flux? It is E into A, right? And earlier we just found what is E? Q by A epsilon naught, and again A cancel, and I can write flux is equal to Q by epsilon naught, which is, we know that expression, right? So we assume that Q charges were there initially inside the capacitor. That is, when the capacitor, the charge and discharge, this charge can what? Change, right? That means when the charge variation happens, there will be a current. I is equal to dq by dt, right? This expression you know, right? Now we just wrote flux is equal to q by epsilon naught, right? Now I'm going to differentiate this so that this becomes d phi by dt is equal to d by dt of q by epsilon naught. Clear? Now d phi by dt then is equal to 1 by epsilon naught, which is a constant term, dq by dt. Now we just found dq by dt is what? Current. So 1 by epsilon naught current, or I can write I is equal to epsilon naught into dq by dt, right? So the current which is there in the capacitor due to the variation in the electric field inside the capacitor is given by this expression, I is equal to epsilon naught dq by dt, and this is known as displacement current. It is called displacement current. Now good thing is displacement current has been removed from your 2020-2021 syllabus of physics. But guys, I don't think without explaining displacement current there will be any meaning of taking Ampere's Maxwell's law. This is the next topic. So this doesn't make any sense of removing this topic from your syllabus. Clear? Right. So we are moving. What do you mean by Ampere Maxwell law? Right. It is an improved form of Ampere circuital law. See, earlier Ampere circuital law, there was only one current, right? We only learned about one current. So before telling about the law, I will tell about something about currents. So one current which we have always learned is current which is due to the flow of charges, right? And the current due to the flow of charges, that type of charges which is commonly studied by us is known as conduction current, right? The type of current which is due to the flow of charges is known as conduction current. But just now we learned inside the capacitor there is another current, right? Which is due to what? Change in what? Electric field, right? Change in electric field caused another form of current. Okay, the changing electric field caused a current which is known as what? Displacement current, right? So in any scenario, when you consider the current is actually combination of conduction current and displacement current. the displacement current is written by ID and conduction current is written by IC. Clear? This should be in your mind. Clear? Now, so again we are moving to the what is known as Ampere Maxwell's law. So initially we had what integral as per our Ampere circular law. It was just mu naught I, right? Now we just wrote total current is actually a combination of conduction current and displacement current. So we have to write it like this. So it will be mu 0 IC plus mu 0 ID, right? So now I can write, we just found the value of displacement current as what epsilon naught d phi by dt, right? So I can write this term as mu 0 IC plus mu 0 epsilon naught d phi by dt, integral b dot dl. So this is the expression which is Ampere Maxwell's equation, right? That is the total integral b dot dl is equal to mu 0 naught conduction current plus mu 0 naught epsilon naught what displacement current. Clear? Simple, right? Now what is the relevance of this displacement current? See, that means if I just draw the displacement current and conduction current as per the capacitor, it will look like this. There is conduction current here, right? And there is a displacement current here, and there is a conduction here, right? So in the case of static electric field, right, that is static electric field means the electric field is constant, it doesn't change with time. So in that condition displacement current will be equal to 0, right? Whereas time varying conditions the electric field will not be constant, will be changing, right? So in that case ID is not equal to 0. So there are some conditions where IC can be 0, ID can be 0, like that, vice versa, right? So when you consider a capacitor, outside the capacitor the conduction current is maximum and the displacement current is 0, whereas inside the capacitor the displacement current is maximum and the conduction current is 0, right? So if I consider the earlier, you remember Maxwell's example, or how he wanted to falsify or found fault in the Ampere circuit law, he took two examples, right? He found magnetic field at a point P and on the side of a capacitor, right? We are taking the same example, right? Here the Ampere law, sorry, this is the point P, right? So remember it was integral b dot el, right? So integral b dot dl is mu 0 I, here what, it is outside the capacitor, so I'll write IC. So b is equal to mu 0 IC by 2 pi r, right? Now in the second case it was like this, right? The point was here itself, but my Amperian loop was like here and the P was inside the hole like this. So I'm going to consider inside of the capacitor. So integral b dot dl is equal to mu 0 I d, because inside the capacitor it is displacement current. So b is equal to mu 0 id by 2 pi r. So there is magnetic field at the point P, right? Clear? Right. Now the last before, see, after this topic we'll do a little bit examples or problems, right? So next section actually is different, that is we have to learn a little bit different, which we'll take in the next class. So that is the last theory portion of today's video, that is Maxwell's equation, right? Actually Maxwell's equation is not actually created by Maxwell. It's actually a set of 4 equations given by 4 different scientists, right? And these 4 equations were combined and then it was stated by Maxwell. So that much important, because earlier the 4 equations were different and described by 2 different scientists, and they were described as 4 different fields, or actually 2 different fields. So Maxwell got or brought up the connection between electric and magnetic fields, right? So that's why these 4 fields or 4 equations were combined and termed or named after him. So the first equation is, this is not all something we have learned itself. Integral E dot ds, okay, integral E dot ds is equal to q by epsilon naught. What is this equation? Remember, this Gauss's law in your electrostatics, right? Now the second law, integral B dot ds is equal to 0. Again, it is Gauss's law in magnetism, alright? Sorry, integral B dot dl, right? Now third equation, integral E dot dl is equal to minus d phi by dt. This is also something you have learned, right? This actually again you have learned, right, in electrostatics itself. That is Faraday's Lenz's law, right? Now similarly, what was the fourth equation? Integral B dot dl, which you have just learned, that is mu 0 ic plus mu 0 epsilon naught d phi by dt, and this is Ampere Maxwell's equation, and these four equations are combinedly known as what? Maxwell's equation. Clear? Now there is a small thing which you have to learn. It was experimentally found that this is something you have to learn in numerical problems itself, that is velocity of light is equal to 1 by mu 0 epsilon naught, where mu 0 and epsilon naught is what? Mu 0 naught is the permeability and epsilon naught is permittivity of free space. So velocity of light in air is equal to, there is an expression like this. So this value was experimentally found, guys. Okay, question we will see what has been asked. In an electromagnetic wave in free space, the root mean square value of electric field is ERMS is equal to 6 volt per meter. The peak value of magnetic field, that is B, is asked, that is P naught is asked. So what is ERMS, guys? It has been given as 6 volt per meter. Now you know what is E by B. Velocity, selector, etc. you have taken. It is E by B is equal to C. Why did I take C? This has been mentioned that it is free space, so I am going to take velocity of light in free space, right? So ERMS by BRMS, I can write it as C, right? So BRMS is equal to ERMS by C, or ERMS I can take it as what has been the value given. ERMS is given as what? 6, right? Now let's not take the calculation now itself, so I can write BRMS is equal to what? Peak divided by root 2, or I can say peak value is equal to root 2 times BRMS, right? Now I can write in place of BRMS this value, that is ERMS by C, right? So now I just have to substitute the value. It is root 2 times 6 divided by 3 into 10 to power 8. I can cancel here. 2 root 2 into 10 to power minus 8. 2 into 1.414 into 10 to power minus 8. 8, 2, 8, 2, right? 2.828 or 83 I can say into 10 to power minus 8 Tesla. That's your answer. Clear? Now let's do the next question, guys. Let's take this one. Let's do the third question. What has been asked? A radiation of energy E falls normally on a perfectly reflecting surface. The momentum transferred to the surface is. Now how would I cancel or calculate it? This is my surface. So first the beam goes here, then it is reflected like this. So you are asked what is the change in momentum, right? Momentum transfer means you are asked actually what is the change in momentum. So when the momentum, I can just, you know what is energy is equal to mc squared, right? Or I can write mc into c. What is mass into velocity is momentum into velocity. Or I can write p is equal to e by c. Right now, as the surface is perfectly reflecting, when I consider first momentum, right, it will be e by c, that is p1 will be e by c, right, falling. So let's take it as e by c. when it goes back, it will be minus E by C, the direction, right? So a vector form, momentum is a vector. So P2 will be equal to what? Minus E by C. Now change P1 minus P2. I will take it as E by C minus E by C, or it is 2E by C. Clear? And which will be the option? 2E by C, the option A. Clear? Now next move on to the next question, which has been asked. Light with an energy flux of 25 into 10 to power 4 watt meter per meter square falls on a perfectly reflecting surface at normal incidence. If the surface area is 15 centimeters square, the average force exerted on the surface is. Now this is a different question, guys. I'll write it here. How can I solve the fourth question? Now you know power P is equal to F into V. I've taught it, right? So I can write force is equal to momentum by, or power by velocity, and for what it is power. Right. Now you have been given watt per meter square, means you are given power into area, or power by area. So if I multiply here with area, can't I get P itself? Right. And then I have to write C, because velocity of light is given. Right. So now it is reflecting, means here it is touching, then it is going back, means when you write power, you have to write it as twice. It is coming, then it is going. You are asked what is average force, so you have to take both the conditions, right? So 2 into what is power by area given, 25 into 10 to power 4, into what is area given, 15 into 10 to power minus 4, because centimeter square is given, whole divided by 3 into 10 to power 8. Right. So what you will get the answer, you will get it as around 2.5 into 10 to power minus 6 Newton. Clear? Right. Now let's move on to the next question, guys. Can I take this one? Okay. We'll bring it up. Right, this is the sixth question. The electric field associated with an electromagnetic wave in vacuum is given by E is equal to I vector 40 cos k z minus 6 into 10 to power minus 8 t, where E, Z and T are in volt per meter and seconds respectively, the value of wave vector. I hope you remember the wave equations, guys. Without that you cannot solve it. So if it is E, this is electric field, right? So E amplitude I cos omega t minus kx, right? I wrote it as because it is in the x direction. This has been given, right? We're going to compare these two equations, guys. So you can compare and you can find omega is what? 6 into 10 to power 8 omega t, right? Then k, remember, it is 2 pi by r, right? Or you would have learned it as omega by c. So you have right omega, right? So what is c? This velocity of light, right? So I can write omega is 6 into 10 to power, it is omega by v or omega by c velocity. So 3 into 10 to power 8, you will get 2 m raised to minus 1. That is the value of k, right? Wave vector, this and all is actually linked with your 11th portion, not a big deal. Clear? Right. But actually the transformer section we would have completed in the theory of our light class, right? So we'll do the transformer, some of the problems, because sometimes I don't think we'll have time for it. Okay, what is the question? The first question: a transformer having efficiency of 90% is working on on 200 volt and 3 kilowatt power supply. If the current in the secondary coil is 6 ampere, the voltage across the secondary coil and current in the primary coil. So I hope you understand what is primary and secondary coil. right? Now what is our efficiency? It is output by input. So output power is, okay, sorry, it is secondary section, right? Voltage into current in secondary divided by voltage in primary into current into primary, right? So yes, okay, so that is efficiency. So how much it is? 90 percentage means it is 0.9. So I will write as 0.9 is equal to Vs into what is secondary current. It is given as 6 ampere divided by what is the power I have been given in the case of primary section. I have been given 3 kilowatt, that is 3 into 10 to the power 3, right? So I can calculate Vs from here. You will get Vs as how much? 450 volt, right? This much you will get, right? First we are doing simple questions, then we'll go over complicated ones, right? So Vp Ip, right, is given as 3000, right? This one, as per this one, or I will write 10. So Vp and Ip, so out of this I find Ip, that is 3000 divided by Vp, right? What is Vp? It is given as 200, right? Primary voltage. So it is given 300,000 divided by 200, you will get 15 ampere. Simple, right? Now we'll do little bit complicated sections, guys. Right. Now suppose, what is the second question? Sorry, I didn't do the second one. What is it? A primary of a transformer with connected to a DC battery of 10 volt draws a current of 1 milliampere. The number of turns of the primary and the secondary windings are 50 and 100 respectively. This NS and NP and NS are given. Voltage in the secondary and the current drawn by the circuit in the secondary are. It is very easy, sir. Transformer is essentially an AC device, right? So you are having DC source, means there will be no mutual induction, right? So second E2 as well as, that is a voltage in the secondary and the current drawn by the circuit, right? There will not be any output. So E2 as well as I2, or ES and IES secondary section will be 0. Yeah, simple question. Now let's move on to the 33rd question. 220 volt input is supplied to a transformer. The output circuit draws a current of 2 ampere at 440 volts. If the efficiency of the transformer is 80%, the current drawn by the primary windings, that is, you are asked what is IP. Clear? So here in place of secondary I will write it 2 and primary I will write 1. So secondary, oh sorry, why is not writing? By primary is equal to efficiency into primary current by secondary current, right? So I can write it as, actually you have written, right, secondary power by primary power is equal to our efficiency. So you are given V1 as how much? 220 volt primary, and I2 has been given as 2 ampere, right, and V2 is given as 440 volt, right? Then I can find I1. How much? This one, that is V1 into, or sorry, it's not V1, right? It's V2 I2 divided by V1 into divided by 0.8, right? Or I can write 10 by, no, this 10 by 8, right? I removed it, okay, 0.8 here, I just multiplied 10 and here 10, that's why, right? Because it is easier to calculate in this way, right? You will get around 5 ampere, right? That is your primary current. Simple, clear? Now we'll do the simplest next question, 33. Oh, 33 we finished, huh? What is 34 question? So as you can see, the transformer sections problems are very easy, guys, because only simple formula is there. So as per that simple formula, the calculations will be very simple. Okay, so I did that problem section from because I don't think I will get the proper time for doing transformers during the live class. Okay, so transformer section problems you can even see in your textbook. Okay, please solve it by yourself. Okay.